Now I'd like to introduce Max Auffhammer, who's Associate Professor of Agricultural and Resource Economics, and his research focuses on environmental and resource economics, energy economics, applied economics, and the economics of climate change. I learned a new term yesterday watching one of his YouTube videos, the carbon mountain, that I'm going to use. So please welcome.
I'm not going to talk about the carbon mountain today, but if you want to hear about it over lunch, catch me when I have a sandwich in my hand. So we are often criticized for not being clear as scientists. I think Todd is one of these model clarity science presenters. I thought that was fantastic. Now you've got the German environmental economist, so we'll see how we do. Hold on, let's make these slides pretty. I worked so hard on those. Here we go. All right. So what I've been working on with several co-authors who will get their due credit in about 4 minutes for about a decade now is what's going to happen to rice globally, recently with a real focus on Asia over the next century. And the approach that I've been taking and a lot of my co-authors have taken, we look at actual data, so there's very little modeling. Most of it is actually looking at observed trends and outcomes. So just to give you an idea here, so rice may very well be the most important crop on Earth. It feeds more humans than any other crop. 90% of all rice in the world is produced in Asia and consumed there as well. And the number that always gets me, I've pulled this number out many, many times, but it receives 24 to 30% of the world's developed freshwater resources. That's a staggering amount of water. It's produced mostly in irrigated systems, so think pumping of water or water coming in through surface water irrigation channels. Those are the high-yielding environments, and we'll make a distinction between that system and the others in a second. And the rest of the rice comes from rain-fed lowland, flood-prone, and upland systems. These are mostly low-productivity, rain-fed systems where the yields are significantly lower, but a lot of that rice is subsistence rice where people grow it to actually eat it and survive. So just to give you an idea here, rice growing systems receive water from above. This is rain-fed rice. Each dot here talking about the metric system. These are hectares. One football field is about a half a hectare. So each dot here is 20,000 football fields. All right, so this is a huge amount of area growing rice. This is rain-fed, so this is water coming from above. If you look at water coming from below or through surface channels, this is irrigated rice. So you can see northern and coastal India, but really I think that the astonishing thing here is if you look at China, I'll give you that one more time right here, the difference between these two. And these are, not guesses. This is satellite measurements of where rice is grown. So just to give you an idea of what this means. So I read a lot of boring web pages on a day-to-day basis. So I really like the FAO Rice Info homepage. I check it daily on my phone. But one thing we want to worry about here is there's a noted deceleration in the growth of rice production. So we're talking about growth rates here, not the level of rice production. And this could be a cause of concern in terms of world food security. I also want you, and Claire is going to talk about these issues in more detail this afternoon, but we should always think of food security as a very much local phenomenon, not necessarily global calories demanded versus global calories supplied here. So is this really true? Kharif here, this is wet season rice production for India's states that are mostly rain-fed. So here's some actual data. Blue is observations, green is a smoothed line, so blue is data, green is science. But what you're seeing here with the smoothed line is if that thing looks like a salad bowl, that means growth rates are increasing. So what we're seeing is through the mid-'80s, and this is largely due to what was accomplished during the Green Revolution, you see these growing growth and output, and then over the last decades or so, growth rates have really come down and slowed down, and output has sort of leveled off. There are good years, there are bad years. But has Max pulled out, rain-fed rice in a couple of selected states in India, or do we see this more broadly? So if we look at crops across the world, this is FAO reported data that you could download on your cell phone. They have an app. And actually look at it. So what you're seeing top left is rice, top right is wheat, bottom left is maize, bottom right is sorghum. Red graphs are China, blue is India, green is Asia average, and black is the global average. You're seeing similar pictures for all crops. Maize, not so much, and we could talk about that over break here, but you're seeing this sort of slowdown in growth rates for all crops. Soy looks very similar. So what I focused on here, and I'll put this in perspective at the very end here, is really how climate change has affected rice through the observed record here. Now, this gets really sort of picky, and you spend years on really tiny aspects of this question, and then at the end of a career you put this together in a couple of slides. But what we're trying to do here is climate is not climate, right? To me, climate has many, many dimensions that matter to the rice plant. So it's temperature, it's humidity, it's water stress, and CO2 fertilization here. So rice turns out to really not like warm nights. It doesn't mind hot days so much. Lower relative humidity causes trouble for rice because it can't transpiration cool. This is very similar in concept to the air conditioner comparison that Bill mentioned this morning here. Rice plants are amazing, amazing plants. So if you need to read some stuff to get an admiration for what these little plants do over the growing season, it is absolutely fascinating to the economist at least. The big issue that we read a lot about in newspapers, and this affects the sort of poorest farmers here, are the issues of drought when there's no water, submergence when there's too much water, or worst case scenario if there's saltwater intrusion, meaning the water you get actually has salt in it. Rice plants don't like any of this, and in most cases these die. There's been quite a push on submergent-tolerant varieties, and there's a nice randomized field trial that ran out of Berkeley, little plug, that actually examined a new variety that does pretty well during submergence and does equally as well during non-submergence time, so a win-win situation. CO2 fertilization is the big unknown right here, is how does the rice plant respond to CO2 fertilization? And the tricky question that we're sort of thinking about now is what's the interaction between CO2 fertilization and temperatures, right? If it's hot outside with a lot of CO2 versus not so hot, how does that work? And it's a very sort of subtle question. But the picture I like to bring up here, when we started looking at this about a decade ago, there are lots of people working on rice, but if you look at the literature that actually tried to correlate rice outcomes, meaning yields, with weather realizations, there were very, very few papers out there that actually did it. And this was sort of the best paper in the literature. And what you've got here is about a dozen observations that correlated different measures of how well the rice plants does to maximum temperature, minimum temperature, and radiation. So these are experimental farms where you get sort of one observation per year, and you sort of see how that does over time. This is, to me, a good example of a really, really important subject that is very much understudied. So what did we do? I was one of two lucky economists that got to work on this. This was the last year of graduate school, and I've been busy on this ever since. Economists are very different from physicists when we think about behavior. A lot of my physics colleagues, in the models, behavior comes out of a hose somewhere or an equation, right? Economists are a little bit more subtle about this. For us, the natural environment often comes out of a hose, so just as bad. But what you want to think about is these are farmers putting rice into field, right? This is not an experimental setup. These are individuals who have a parcel of land who have to decide how much rice they plant at the beginning of the season. So they may look at how much was rice sold for last year. Does the government guarantee me a certain minimum price? How much does labor cost this year? How much does fertilizer and pesticides cost this year? And how much of my area did I grow rice on previously so I don't have to redo my fields? So that goes into the decision on how much of your area you should plant to rice, and then you put the rice plants in, and then you pray, right? So what you're praying for is you're praying for really good climate outcomes. You're praying for the monsoon to arrive on time and ample water at the right time. You can do certain things to help with bad or good climate outcomes. You can add more or fewer pesticides. You can send out more or less labor. But essentially, when this stuff is in the ground, you are dependent on the environment. So you put this all together in what we call a production function. You combine the natural inputs and the sort of socioeconomic inputs, and that determines how much rice comes out at the end of the day. But the takeaway message here is, in between climate and output, there's a farmer that takes actions. And what actions the farmer takes has huge impacts on what rice gets produced in the end. So I'm going to summarize 3 papers here. If you're interested in this, I'm happy to send you more than you could read in a month. But these are 3 papers we've worked on that really looked at this question of, throughout Asia, how sensitive to what weather outcomes is rice, and what does this mean for a world of climate change. So this was all motivated by a person named Ramanathan down at the Scripps Institute of Oceanography, who worked on something called then it was called the Asian brown cloud. That was not a popular name for it. It's now called the atmospheric brown cloud, which preserved the acronym but made it more politically palatable. But what you're seeing is you're seeing a view of the Taj Mahal taken with a bad camera on a bad air pollution day. This is the view of air pollution from space. You can sort of see it cover, most of India here. And if you want to zoom in here, here's another nice view from space of what air pollution looks like. And here's another nice view out of the airplane window. Many of you have flown into Mumbai or similar places. If you've ever flown into Inner Mongolia, it's a really impressive amount of air pollution that you fly through. Why am I showing you this? This is a climate change talk. This air pollution has a really interesting impact on the climate that you observe on the ground. It bounces back solar radiation into space, so you get less solar radiation on the ground. You also get a cooling effect on the ground. And what you also get is you get a warmer atmosphere. Warmer atmosphere is more stable. A more stable atmosphere holds more water. At least that's how this economist understands it. What does this mean for the rice plant? Well, what this means for the rice plant is the following. You get cooling on the ground, right? So this is good for the rice plant. But what's bad is you get less rainfall, you get less solar radiation, and if you have global warming going on at the same time, you get warming offsetting some of this cooling effect. Now, the thing economists and graduate students like is if the answer isn't clear, because you could publish either answer you get here. So what we've done for a long time now is try to quantify the magnitude of these weather sensitives on rice output to figure out going forward what's the impact of climate change and air pollution affected local climate on rice output throughout Asia. So the first thing we did, I'm skipping about 4 years worth of work and just putting one picture in here. What we essentially did is we collected data for a 30-year period throughout India on observed rice yields, area planted, and weather outcomes. This took a long time in Berkeley's archives, and we've correlated rice yields with these weather outcomes. So what we found is that indeed observed on-the-ground rice likes cooler nights. So there's a significant penalty of getting warmer nights, and rice also really likes more rainfall during the monsoon season. So what we were able to do is not just say, well, this is sort of obvious, but we were able to quantify how big that impact is and model how big that impact was ex post, looking from 1960 to 2000 in terms of the local climate-induced impacts on rice output from just regular climate change and this air pollution-induced climate change. So the numbers, depending on what time period you're looking at here, are somewhere between 8 and 15% in terms of total rice output. Some of that mechanism worked through farmers abandoning their fields because rice is no longer a profitable activity. Some of it happened through worse yield outcomes. So it works along two margins here. The thing I'm most excited about, that the referees really gave us a hard time on this one, but we convinced them finally with lots of data collection here. What has been hypothesized in the literature that it's not just the total amount of rainfall that matters for rice, but it matters when the rain comes, right? So if you have a certain amount of monsoon rainfall over the monsoon season, if all of that rainfall falls in 3 days and in between you have drought, versus if that rainfall comes nicely spaced out every couple of days, those are very, very different mechanisms as to what's going to happen to your rice plant. So what we did is we have this very nice gridded rainfall daily data set over India. And what we've done is we've looked at the frequency of drought, we've looked at the frequency of days of extreme rainfall, and we've looked at the overall amount of rainfall that comes down during the monsoon season. So what you're seeing here in the blue line right here, you're seeing a drop at about 1960, which is when we think sort of air pollution got really bad and global warming effects were detectable. You see a drop in total rainfall. The green line right here is, that's the extreme rainfall right here. So you see a trend in extreme rainfall events. And the red line right here is October, November total rainfall, which also goes down a little bit. But we're seeing, and there's an active debate in the literature as to how significant this effect is, but we're seeing changes in monsoon rainfall pattern already. So what did we look at? We tried to translate this into rice yield impacts. So I would yell at my grad students if in front of an audience like this, they'd throw up a table like this in 8-point font that's kind of blurry. What you're supposed to take away from this particular figure is we broke down from our previous project the effect of overall monsoon rainfall into the role of total rainfall versus how many days of drought versus how many days of extreme rainfall. So what we learned is less total monsoon rainfall is bad for rice, more drought is bad for rice, and more extreme rainfall is bad for rice. And the nice thing about these econometric studies, these statistical studies, is you don't just get the quantitative, the direction of the impact, but you actually get a number for it, so you can simulate what this means for rice. So overall amount of rainfall is really significant, but you can see that the coefficient on drought here is roughly the same size as that of total monsoon rainfall. So drought is really, really bad for rice output. Now, last project I'm going to talk about in my last 2 minutes before I'm going to have some depressing closing remarks is together with IRRI, which is the Rice Research Institute in Los Baños in the Philippines here. We got access to a data set which surveyed farms over a number of growing seasons throughout Asia's main rice growing regions, and they asked the farmers everything. What type of rice did you plant? When? Which member of your family was on the field? When? How much irrigation water was applied? When? And they put an actual weather monitor on these sites. So it's a dream data set. I have more categories. I know more about these farms than I can actually use in a statistical model. But what we did, and this is now irrigated rice, is we wanted to figure out at different phases of the rice plant's life. Much like we do, we have very complicated different life stages, right? The rice plant does too. We looked at different stages of the irrigated rice plant's life, what type of weather matters in what way. So the goal here was to help people who come up with new varieties of rice design new strands of rice that are resistant to negative weather outcomes at the right part in the rice plant's life stage. So I'm not going to bore you with this picture very much, but what we're seeing is that warmer nights are bad for rice during the vegetative and the ripening phase. We're seeing that more radiation during the ripening phase is good, and hotter days are actually okay during the vegetative, the reproductive, and the ripening phase too. This is consistent with what rice breeders tell us. They don't even worry about sort of extreme daytime temperatures. They worry about nighttime temperatures very much. So in my last 2.5 minutes here, we've learned a lot about rice on ag. We've learned a lot about climate on agriculture, but having recently been given the chance to survey this literature under the brave guidance of Chris Field right here, and we can't talk about it yet, there still is a lot of open territory here for further research. So we know that radiation matters, that whether it's cold at night or during the day really matters, when the rice plant is exposed to extreme weather matters, and also that these responses of the rice plant aren't linear. A linear world is really beautiful because it's easy, but they're highly nonlinear and often non-symmetric, which makes it tricky. But we're already observing substantial impacts on rice and certain other crops in areas, and reduced climate change we showed would boost yields, and we think more than we've so far predicted. Now, big picture thoughts for closing were the instructions. So rainfall clearly matters for rain-fed agriculture. I don't need to tell you this. This is sort of obvious right here. But what we do not model anywhere here is the availability of water as a backstop technology. So if you're rain-fed and your neighbor has a pump, you can sort of pump in water in really bad scenarios or bad monsoon seasons in order to overcome this particular shock. So there's this availability of backstop water, and what I mean here is large amounts of irrigation water in a drier world and drying regions. So the issue here is we're really worried about reliability of irrigation water supply, right? And we've talked about snowpacks, and I will again in a second, but groundwater supply is heavily impacted by falling water tables. You're going to have to drill deeper and deeper and deeper, and more extractions will lead to more and more dropping, more rapidly dropping water tables. And surface water supply, the stuff that now comes down nice and smoothly from the snowpack in the Sierras and the Himalayas, if it gets warmer, there'll be less overall water, and it'll come down really rapidly during certain parts of the year, and then maybe much less or none at the end of the season. So this is one scenario that we won't like. The other interesting linkage, there's a lot of talk about the energy-water nexus here. In India, 2 summers or 3 summers ago, what brought down the grid? It wasn't air conditioning. It was irrigation water pumping, right? It was hot, farmers were pumping, brought down the grid. The social costs of such an event, we can't measure, right? But they're certainly significant. So we've seen this picture 3 times today. Mine's the worst version of it, but we're very much worried about snowpack in California. What I want to leave you with is, yeah, I know, we've seen this picture 1,000 times. What's he going to say about this one? Oh, and this is a bad version of it too. But this is India. Hold on, where are we? Yeah, this is India right here. So you have about 600-700 million people living in the Indo-Gangetic Plains that rely on their water supply from the Himalayan snowpack. So what we're really, really worried about here is all of a sudden 600-700 million people that rely on this water for their daily livelihood no longer having that reliable source of irrigation water and water for other uses. This is obviously not just true in India. This is true in any area that relies on the snowpack for its water supply. So if we take a step back for a second and think about what are the big impacts here, food security, that's the sort of obvious one, but I think population is the one that nobody's really willing to talk about here, right? So the climate impacts here are going to big on rice yields, but they are dwarfed by uncertainty as to whether we have 600 million or 1 billion people living in the Indo-Gangetic Plains relying on a potentially unregular or unsure supply of irrigation water. So Malcolm's going to talk about this much more this afternoon, and I've done my part, and I thank you for giving me 2 minutes and 18 seconds that I went over. Right.